In this video, we're going to cover 4.2 and 4.3 and 6.2. It's all kind of the same idea, just extending on this idea. I will break this up into two videos, so hopefully they're not too long. To start off, let's recall, and this is like some first day stuff you may or not remember, y prime minus 3y equals 0. And we thought about solving this on day one. And we thought about it as y prime equals 3y, and we sat and debated, what function when I can take my derivative and get the same thing but times a constant multiple. And the first thing that came to our brain when we were doing that is like e to the x spits back its derivative as itself. So we checked out that solution, and in that time it turns out that it was it. So it is natural for us to ask, when I have a dE that has coefficients that are constants, maybe the same idea will work. And it actually does. So the solution we are going to consider is, so let's write this out actually. Consider y equals, and we're going to do e to the mx. And we're going to plug this in and see what happens, and see if we can maybe come up with a solution this way. Just on the intuitive approach that this worked up here, maybe this will work down here. So evaluating we have, all right, so I have y, I need y prime. So y prime would be m e to the mx, right, chain rule. And then I also need a double derivative, right, second derivative. That's going to be m squared times e to the mx. So let's plug all this in. So the y double prime is m squared e to the mx minus 4 times the derivative, which is m e to the mx, and then plus 3 times e to the mx. That equals 0. That's just plugging in. If this solution, we can make this work or think about how to make it work. Notice that everything has an e to the mx. So I'm going to factor out e to the mx, leaving me with m squared minus 4m plus 3. Now, back to pre-calc 1. When we're solving something like this, I have two things multiplied to equal 0. One of them have to be 0, right, for it to work. This term here, e to the mx, is not going to ever spit out 0. Now, we know that's a solution, possibly. We're looking at it. But I know I'll never get 0 there. Any m, any x, I can't get 0 out of e to something. Negatives give me a fraction, 0 gives me 1, positives aren't going to give me anything else. So what this tells me is that m squared minus 4m plus 3 is equal to 0. So we just have a quadratic to solve. We could actually have a solution. We just showed that it works. That when I plug in e to the mx, I got down to this, and now if I could just find the m, then I would have a solution to my dE. So this is just quadratic. We could use a quadratic formula. We could use factoring. Those are typically the two we go to. You could complete the square. You could also graph it. Nobody chooses that. So here we go. We got m minus 3 times n minus 1. That will get me 0. Zero product property, again, tells me that m minus 3 is 0, or m minus 1 is 0. So m must be 3, or m must be 1. Now what that means here, these were m's, we actually get two solutions. So two solutions to this dE. We get y1, we'll call that. We get e to the 3x, and we get y2, which is e to the 1x. We have that both of these are solutions. These are actually linearly independent, not dependent on each other. There's no constant multiple that I can multiply to get to the other one. So this is our FSS, right? This fundamental solution set, which means I can write a general solution because it's a second order. My general solution that will cover all solutions is C1 e to the 3x plus C2 e to the x. So I feel that these are some of the easiest type of dEs to solve. given this chapter, given everything we've done so far. When we have constant coefficients in front, we can actually do this method to get down to here. Now, a couple things I do want you to notice, and I don't want you to rely on this. It's better to work it out every time so you'll know why. But notice that this is almost the same as that, but we were to replace all our y's with m's, right? M squared, m to the first, and then no m at the end there. You could jump to that. I would prefer you at least state it. Say, I know, okay, so what this thing is called, we should name it. This thing here is called the characteristic equation. Right here. So if you can jump straight to the characteristic equation, you could say, since this is a homogeneous linear ODE with constant coefficients, I have the characteristic equation is blah. Now, we want to see, is this going to work all the time? Can I always rely on that? We did a very specific case. Let's take a very general case here. So solve the DE. So we have this same idea, except for now we have constants A, B, and C instead of the numbers that were there. So we have a couple cases. We could solve the characteristic equation here. And I'm not going to do so, but if you plug in y equals e to the mx, and you plug this in and you solve for m, right, we get down to our characteristic equation, which is going to have am squared plus bm plus c. If you want to see why this works out, plug this and y prime, right, m e to the mx, and y double prime, which is m squared e to the mx. I would encourage you to plug these three things in and work it out down to this and see if you can get there. You can. It's the same as example 1. It looks almost identical, except for now it's going to have an A, B, and C. It's the same idea, just shuffle around those A, B, and C's. We have 3 cases when dealing with a quadratic. I don't know if you guys can recall. The first case, so case 1, is that m1 and m2 are real numbers. That's what we want, right? They're 2 real solutions. If you relate this back, remember this is a parabola. When we have 2 real solutions, that would be like on our plane, we have some kind of quadratic where it crosses twice, right? That was based on our determinant as well, if you wanted to use that. But in this case, what happens if you have an m1 and m2 that solve our equation, then our 2 solutions are y1 and y2, and we just throw m1 and m2 in there for the coefficient of x, giving us a general solution of that. It's actually, I think, the better scenario. It's the easiest one. Now, the second one, m1 and m2 are real numbers again, but this time they equal each other. That means there's a repeated root. If I think back to my quadratic, that would be when my quadratic is sitting on the axis. We get what's called a repeated root. It comes from something called multiplicity, if you remember that, but like the multiplicity of this power of negative 3 is a root here, has a multiplicity of 2. So that means it actually bounces off like this does up here at negative 3. So we're looking at repeated roots. If that's the case, this one isn't as straightforward. You can come up, okay, so here's this one, and then this second one is what I was about to tell you guys. Notice it's just the first one times x. You can see that this is done if you start here and use reduction of order. You can find y2 assuming that you just let some function in y1. It's the whole reduction of order. I'd recommend you going through that while you're watching this video. Go ahead and stop and try to use reduction of order starting here and coming up with that one. I would encourage you to do it. It's good practice. You're going to get quizzed on it anyway, so you might as well practice. And then we end up with our general solution by taking those 2 things and putting them in front of C1 and C2. These are really nice when that happens. You can also check these as you're plugging them in, or as you're doing it to try and make sure it makes sense to you why they would work. Okay, case 1 was when the 2 solutions were real numbers. All right, let me start erasing this highlighting. Case 1 was when they were real numbers. Case 2, we just did it. They're real numbers, but they're the same number, so I have a repeated. And then case 3 is that they're imaginary. Right? That's the other case for this parabola. That would be maybe when the parabola is up here or down here, right? it's not crossing through the x-axis at all, so it has no real roots. They have what we call imaginary. Now, the imaginary root will always look like this. Right? We get an a plus bi, a minus bi. That's that complex pair. They always come in pairs. So we have m1 and m2. So if I were to try to set this up, what we would want to write, if we take a look, it's just e. Remember, we take this answer and put it in front of x, so that's what we did here. Now, that's not a great answer because the complex really doesn't speak much to us in the real plane. So we can actually use Euler's formula, and I'll show you where that's at. So y1 is equal to this. We're here. I actually here will distribute the x, so the x goes to both. Then I can separate it here because, like, if you remember, x to the second, x times third is x to the fifth. I add my exponent, so if I'm going backwards, I can actually start at x2 plus 3 and get back to that. So that's what they did here to here. All right, and then this is Euler's formula, and you may not know that, and that's okay, but Euler's formula says this is equal to that. This is where the e to the pi I come from, equals -1. I don't know if you guys have ever heard of that. I think he called it the most beautiful equation because it contains most of it. Look into that if you're interested. If not, we're using Euler's formula here to come up with that. So e to the beta ix, all right, and then I switch it to that. And then notice you could just multiply e to the alpha x to both, and there is y1 expressed as a real part and an imaginary part. Where these solutions come from is we actually just take those real parts and there are solutions. So y1 is the real part, y2 is the imaginary, without the I. So to write a general, we have that. So if we end up with complex roots, we follow this method, and we can spit out two solutions. All right, let's do example 3. Let me make sure. I think my headphone just died, so I want to make sure I'm good. All right, give me 1 sec to make sure that's connected. It is connected. All right, so just in case my sound went off, my headphone died, I just plugged another one in. All right, so here's example 3. We are going to work through this mess using the same thing. Notice that we have constant coefficients. That's what we wanted. So we are going to come up with our characteristic equation. How we do that is we start with y. We know it's e to the mx. Then y double prime is m e to the mx. And then y, I said y double, but I meant single. Double prime is m squared e to the mx. I plug all this in here. So I get m squared e to the mx minus 10 times m e to the mx plus 25 times e to the mx. Notice everything has an e to the mx. I'm going to factor that out, leaving me with m squared minus 10m plus 25. And that equals 0. So again, same reasoning. That'll never equal 0. So we're only going to look at what's called the characteristic equation. So we have this quadratic. If I can find m, then I can find solutions. So there's factors. You can use quadratic formula if you need to, but it factors to m minus 5 times n minus 5, which means n is 5. Now, if we take a look at our notes earlier, it said, okay, I get one solution, so y1 is equal to e 5x. y2 is x times e to the 5x. I just multiply it by an x, which tells me that the general solution is y equals c1 times y1, which is e to the 5x, plus c2, y2, which is xe to the 5x. So there we go. So again, I like this method. I think it's straightforward, and all we have to do is solve a quadratic, which makes our life great if we can get down to that part. Now we have one more example, and then I'll switch. It'll be another video for the back half of this. We have an IVP. I'm going to jump to my characteristic equation. It's m squared minus 4m plus 20 equals 0. So I'm just going to write characteristic, if I can spell it right, let's do this. Characteristic equation. My mind drew a blank here. So there's my characteristic equation. So I can just solve that to help myself out. I believe this factors. Maybe not. Nope. 5 and 4, 2 and 10. Okay, so I'm going to use the quadratic formula. M equals negative b. I'm going to write this out first. Plus or minus the square root. Hopefully you have this memorized at this point. If not, shame, 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 shame on you. Get it memorized. It doesn't go away. So negative b, or opposite of b, is how I think about it. I get 4 plus or minus, and then I always do this off to the side. Just to make sure I'm not overwhelming myself with plugging things in and having to recopy. All right, so I get this. I got 16 minus, okay, that's 80. So 70, 64. And it's negative. So I got negative 64 all over 2, because a is 1. So this is 4 over 2 plus or minus 8 over 2i. The negative gets me the I. Square root of 64 is 8. So this is equal to 2 plus or minus 4i. Now, I can use the equations that we just came up with a second ago that were just saying, hey, if I have this, I can come up with my solutions. So y1 equals e to the alpha, which is 2x, times, okay, let's go snag this, cosine beta x. So beta is 4. Okay, y2 is e to the 2x times, I think it's sine. Let's go make sure. Yep, sine beta x. So we get sine 4x. Then my general solution is y equals c1, whatever that may be, times e to the 2x times cosine 4x, plus c2, e to the 2x times sine 4x. All right, we have some initial conditions that we're going to use. Y of 0, I think, is 2/3. All right, and y prime of 0 is negative 2/3. All right, so I have two c's. I'm going to plug everything in to get my c's out. I am going to need a y prime, so let's figure out that first. So y prime, I have a product rule here. I got, we'll do the first one. So 2c1 e to the 2x times cosine 4x. Plus, I leave the first one alone. I'm going to get a 4 here, a negative 4, because it's a cosine. Negative 4 c1 e to the 2x sine 4x. All right, I'm going to go down. Now I'm doing the quotient rule of this thing. So I got 2c2 e to the 2x sine 4x. Then I also have the other way, so we're going to get plus 4c2 e to the 2x. All that stays the same. Derivative sine is cosine. I already took care of the 4 by putting it out front. So there is my derivative. So we're going to use both of these to come up with a system of equations. So starting off, let's deal with the pink ones. I have 0 equals, I'm focusing on here, not 0, but 2/3. 2/3 equals everything with 0 in it. So I got c1 e to the 0. Let's just think through this. If this is 0, that's e to the 0, which is 1. Cosine of 0 is 1, so we get 2/3 as c1. Plus, now I got to plug 0 into this one. 0 for this becomes a 1, and then I get 0. So this tells me that c1 is 2/3. Now I'm going to use the y prime one. I got negative 2/3 is equal to, and now I got to use that long mess. I got 2c1, and I'm plugging in 0. So I get, this will be a 1. This will be a 1. Right? The next thing, I'll have a negative, and then this will be a 1. This will be a 0. So it's gone. This is 0, so it kills that 1. And then the last one, this will be 1, this will be 1. So I get plus 4c2. I know that c1 is 2/3. Right, then I work that out. I got negative 2/3 equals 4/3 plus 4c squared. I'm going to multiply everything by 3. So I got negative 2 equals 4 plus 12c2, which means 12c2 is equal to minus 6, which means c2 is equal to negative 1/2. So my solution to the DE is y equals 2/3 e to the 2x cosine 4x minus 1/2 e to the 2x sine 4x. Right, so there's my solution there. This takes a little bit of work with the C1s and C2s, just like any other IVP, but the solving of the DE up front, I think, is definitely less involved.